Hello everyone, welcome to my lecture today. Before we begin, I would like to ask everyone in this room one quick question. When was the last time you've watched a cartoon? When was the last time you watched a cartoon? Because for me, I remember when I was growing up, I used to live and breathe these shows. Peter Pan, Mickey Mouse, Popeyes, if you could name it, I have probably seen it. And so these shows once held such a special place within my heart that it felt almost irreplaceable. So what changed? Well, as I grow up, I used to find all these shows really interesting because they were magical. However, the older I get, the more ridiculous these stories seem, the less magical they are, and the more absurd I see them. So eventually, my love and commitment to these shows became a mere hobby, then a distraction, until finally a forgotten pastime activity. However, that is until recently. Recently, I had the chance to go to the theater to see one of the newest Doraemon's adventure, Earth Symphony, I think it was called. And I could not help but to feel nostalgic. I could not help but to remember how eager I was to rush home every single day so I could catch the newest episode airing on HTV3 at specifically 4:30 p.m. on the dot. And what's so amazing about these episodes that keeps me coming back was the fact that every single one of them encapsulates a magical adventure, one that is only made possible because Doraemon had access to these magical technology, those that actually bend the laws of physics themselves. And so, as a kid, I was extremely envious of Nobita. I kept thinking to myself, how is a kid so lucky? It should have been me. But that is no longer. That is no more. Because with humanity, as I study physics, and humanity's deepened its understanding of the universe through means like quantum mechanics or other forms of modern physics, the more we learn, the more I found out that these technology are not far from us. And the more I learn, the less magical they feel and the more tangible they become. And so that begs the question, That brings us to my topic for today. How close are we from the technology of Doraemon? And more specifically, how close are we from inventing time traveling or teleportation? Well, the quick answer to this question is we are definitely not quite there yet. However, we might be closer than you think. So, how close are we from teleportation? To answer this part of the question, we first have to see how Doraemon does it. Doraemon, the biggest theme in Doraemon has always been exploration, Him, along with his group of friends, have managed to travel to every single corner of the world, to the depth of the sea, high up in the sky, and heck, even to space. And all is made possible, All of this is possible because he had this magical door that could transport anything, anywhere, no matter what's between them, and no matter the distance between them. Amazing, Just like that. Now, what if I tell you, now imagine how amazing this technology would be if it was real. Imagine just stepping through a door and you're in your favorite cafe, You're on the basketball court, or you're on Mars hanging out with Elon Musk. You know what's even more amazing? What's even more amazing is that scientists are already making this concept a reality. We're actually getting extremely close to inventing something as impressive. However, before we get too excited, before we pack our bags, there's this tiny, tiny problem. Albert Einstein. Albert Einstein would not have liked Doraemon very much, and the reason for that was in 1905, he published a paper called Special Relativity. And in it stated that there was a fundamental link between energy, mass, and the speed of light. He argued that an object with a mass cannot travel at the speed of light because the faster it gets to this velocity, the more its mass starts to increases to an indefinite amount. And consequently, the energy required to push it at that velocity also amounts to infinity. And thus, in short, he would have concluded that Doraemon's method of teleportation is impossible because he is breaking this rule. So does that mean that we are stuck? Well, not exactly. Remember how I said we were close to inventing something as significant? Well, this something lies not in the world of classical physics, but in the world of quantum mechanics, the studies of subatomic particles that later led on to the discovery of a breakthrough, quantum teleportation. So what is quantum teleportation? What makes it possible compared to Doraemon's? Well, it's different in the sense that it doesn't actually transmute matters, but information. And also, it requires much more step as well. So to illustrate it, right, I would like to invite my trusty assistant, Lil Timmy, to the stage. Everyone, please say hi to Timmy. Hi. Right. Now, suppose Timmy wants to send me this Lego man right here. Through means of quantum teleportation, he would not be able to just throw it through a magical door and have it on the palm of my hand. Instead, he'd have to go through a set of procedures that starts out by first breaking down this Lego man into tiny individual pieces. Yes, down to the subatomic particles, down to proton, neutron, and electron. Following that, he'd have to carry out a scan, something we call photoelectrospectroscopy, which is just another way to say that I'm trying to find out the instruction set on how these particles built up this Lego man. And so ultimately, right, Timmy would have to send me this information through a digital channel, so I could reconstruct an exact replica of Timmy's Lego man down to the subatomic particle. And just by tinkering with it a little bit, ladies and gentlemen, quantum teleportation. Let's just stop for a minute, right? Just think about the infinite possibility that this technology could bring to humanity. Traveling to space, traveling through the moon to the moon would be a matter of minutes and seconds instead of days or months. However, once again, before we get too excited, when things start to sound too good to be true, there's always a catch. The catch is, in this scenario, being to teleport something so big like a Lego man that is built up of billions and billions of particles is currently far beyond our level of technology. And the best we are able to teleport are tiny, tiny particles called electrons or a photon. But even to teleport something so small, almost invisible to the naked eye, we will still run into another complication, one that arises from the Heisenberg's uncertainty. The German physicist Werner Heisenberg figured out that it was impossible to find out both the position and the momentum of an electron at the same time. Well, this is because if we want to find out the position of an electron, we'd have to shoot a beam of light at it. And at the same time, it will shoot one right back at us. And by measuring the wavelength, the frequency of the emitted light wave, we could find out its original energy level and thus where it originally was. Well, the problem, when we send a beam of light at an electron, we lose track of its original momentum because we have given it energy, and now we completely lost track of its original state. But in order to teleport, we need both of these pieces of data. So this is where physics stumbles upon a hurdle. And when it seemed like we've reached a dead end, right, Albert Einstein himself, along with two other scientists, Boris Podolsky and Nathan Rosen, they came up with a solution: quantum entanglement, a phenomenon so weird and so unexplainable that Einstein could only describe it as spooky action. So what is quantum entanglement? It is hard to explain how, but it is a really easy concept. When two particles that are said to be entangled, they share an invisible link that allows us that when we measure the characteristics of one particle, we could infer the characteristics of the other. Think of it as if I'm flipping two coins at the same time. Right? If I look at one and see its tails, I immediately know that the other is also tails. But instead of coins, it's actually particles, and instead of heads or tail, it's the quantum state identity of the particle. However, and so that is just what we need to level the playing field with Doraemon. Here's how these concepts come together to allow us to perform something called quantum teleportation. We first have to start out with a pair of entangled particles, which we call particle A and particle B. So to teleport, and the particle that I want to teleport is called particle X, that I want to teleport from A to B. The first step I would do is I would have to perform something called a Bell state measurement, which is essentially measuring characteristics of A and X together to avoid the uncertainty of the Heisenberg's uncertainty, whilst allowing me to deduce the partial information of X compared to A. And at the same time, right, some of X characteristics gets copied onto A, and because A was entangled onto B, it gets entangled onto B as well. However, the information is imperfect. Until finally, right, the last step would be setting the result of the Bell state measurement to the receiving ends at B, so they could form an exact replica of particle X with the information that I've given them. Any questions? Matter of fact, Who here actually understand what's going on up there? If you did, it'll be really impressive. Because when I first came across this theory, it took me a few tries to truly wrap my head around what's going on. But even after simplifying it to this level and revisiting it when I write the script, I still found it really difficult to understand. So with that being said, right, I would like to pass on my experience as a high schooler approaching this phenomenon. I would like to re-explain it in my own perspective. And to do that, I once again need to invite little Timmy back to the stage. Now, instead of entangled particles, imagine if I had a pair of entangled paper. Hold on, guys. Paper A and paper B. Because they are entangled, whatever I write on A will appear on B. And this right here in my pocket is particle X. What I want to teleport from A to B. And so the first step I would take is that I would have to stamp X onto A, just like that, directly in the center. And then I'd have to look at it and assess its alignment to see where it was, which is dead in the center, not top left, not top right, not anywhere else. Remember this information, guys. And immediately when I stick X onto A, which represents spell site measurements, the same shape of X will appear onto B, just like that. However, tiny problem, it is imperfect. The shape might be upside down, it might not be in the center. And so I would have to pay Timmy a call. I have to give Timmy a call. I have to call him, hey Timmy, when I stuck the sticker on, it was directly into center with no rotation whatsoever. So could you fix that really quick? Timmy was like, oh yeah, sure, I got you, bro. And ladies and gentlemen, just like that, quantum teleportation simplified. That is how we beat Doraemon. Yeah, I know it is a stretch to say that we've managed to reach the level of Doraemon by simply teleporting tiny, tiny particles, but still, I know for certain that this technology will be within the grasp of humanity in the near future. But until then, it is 1-0 to the blue talking cat. Wow, that was really content heavy, really complicated, I know. Wait until you get to time traveling. You would think that it's harder, right? You would think that it's way more complicated. But what if I tell you it wasn't? What if I tell you it's so simple that I could do it right here, right now, without needing a time machine? Are we ready? All right, give me 1 second. Right, 3, 2, 1. Hello, ladies and gentlemen. My name is Phong, and I'm from the past. Well, to be more specific, less than 1 nanosecond in the past. But still, relative to you guys, I'm from the past and you're my future. How does that work? Well, before you think I'm some crazy time traveler wannabe, let me explain. Right? It is proven by fact. In 1915, Albert Einstein published another paper. He called it general relativity. And in it, it stated something weird. Right? It stated that time was not the rigid, unchanging constant like we thought it was, but rather flexible. And it can shrink or stretches under the right circumstances. And that the only absolute in our world is the speed of light. Think of it this way, right? Think of time as an extension of space. In our universe, we share 4 dimensions, 3 of space and 1 of time. And these 4 coordinates act together to tell you where you are in the world. Now, for example, right? Suppose I want to ask a friend out to a coffee. There's no point in me telling her where the coffee is without also adding that I'll be there at 6 a.m. on a Monday morning enjoying a cup of cheddar. Because as far as I'm concerned, she may be there 10 hours later looking for me, but at that time, I've already left. And so, much like how you can move through time at different paces, you can move through space at different paces by going faster or slower, you can do the same with time. Now, to understand this better, let's have a thought experiment. Imagine if Timmy was standing still, holding a baseball. However, unlike Timmy, I'm also standing there, but on a fancy McLaren traveling super, super fast. What happens when by the time that I reach top speed and passes Timmy, we are both gonna throw the baseball forward. Now, assuming air resistance is negligible. Timmy's ball may be traveling at 5 meters per second in front of him, whereas mine will be traveling at 5 meters per second plus the speed of the car that I'm traveling in. Simple, right? Newton's first law of motion. Same reason why you don't fall backwards when you jump on a bus. However, what if it wasn't baseball we're throwing? What if we were shooting beams of light? And now this is where things start to get complicated. The speed of light has been proven to be a constant by great minds like Michelson or Morley, and many others in the past. But what if I was going really, really fast on a car, and then I turn on my headlight? Wouldn't that mean that my speed of light is a little faster than your typical light speed? Well, not exactly, right? What if it doesn't actually speed up? Does that mean that Isaac Newton, the father of all physics, is actually wrong? Well, Einstein took a look at this dilemma and he thought to himself, what if both parties were right? What if, although the speed of light doesn't change, something else must have changed to adjust and accommodate for the laws of physics being broken? He argued that this something was time. Time has slowed down or delayed to counteract the change that we have given it. For Timmy, who is standing still, he might be experiencing time normally, but for me, who's traveling super fast, it is just time must have been slower. For Timmy, 1 second could just be 1 second, but for me, it's a mere 0.99 second. And yes, I know what you're thinking, right? This effect is too small to really be significant at all. But the faster you go, the closer you get to the speed of light, the bigger these gaps become. And as ridiculous as this sounds, I promise you guys that these are not something that I made up in scientific facts. Matter of fact, it has been proven before. It has been experimented on before. This is Haffel-Keating's experiment, right? They wanted to prove time dilation, and they did this by having two very accurate atomic clocks. One they kept on the ground stationary. The other one they sent around the world on an airplane that's traveling at approximately 700 kilometers per hour. And you know what they found when the two clocks arrived at the same location? They found that the one that was on the plane was noticeably slower. And mind you, there were no faults with these clocks. And so, ladies and gentlemen, that is how we travel into the future. But what about traveling backwards? Well, unfortunately, the answer is that it is not possible. Although there are hypotheses that suggest this is possible if we travel through a wormhole, through a black hole, or even building a time machine that wraps the space-time continuum itself. However, none so far has been proven, and none has ever been experimented. Matter of fact, none has ever been experimented on at all. And so, with that said, I must conclude that we have not mastered Doraemon's method, any of Doraemon's gadgets at all. However, that is not something we should feel sad about. Matter of fact, we should feel proud because one thing for certain is that the space between reality and fiction is definitely shrinking. And through this speech, I want to emphasize that the difference between science fiction and reality is the mere capabilities of the human mind and time and science itself. And science. So with that being said, thank you for listening to my TED Talk.